Hey YouTube, it's Mike back with part 11 of our operating system tutorial. And this is going to be a bit of a longer one. We're going to split it up into 3 sections. And there will be like a table of contents in the beginning after I'm done with this intro that you'll be able to skip around, and if you're on the phone or whatever, I'll have a timetable in the description. But in any event, we're going to be switching to 64 bits in this tutorial, so it's actually going to happen. We're going to talk about virtual memory and paging, global descriptor table, and then we're going to make the switch. Also, before I begin, just like to say, what I'm about to say, while it makes sense in my head, might not in yours. So if there's anything that you're confused about, I highly suggest taking a look at chapters 4 and chapter 5 of the AMD 64 Programmer's Manual Volume 2, link in the description. And that is super detailed, super in-depth about paging, about global descriptor table, setting up long mode, all that good stuff. And I'm going to reference it a couple times in this video, but just know that that's a great resource that you can use to help make sense of what's going on here. Anyway, with that out of the way, let's get started. The first order of business is paging. So paging is basically, it creates a unique address space in memory for specific applications and tasks. So if I have an application that, I don't know, it does something. I don't need to specify what it just does something. Then, depending on how much memory it needs, it will allocate it will use a certain number of pages that is mapped to physical memory, and those pages are unique to that application, so no other memory can interfere with the memory that the specific application is using, which kind of creates a safe space in a way for that application, so you don't have conflicting memory and stuff. And that's the general idea. And one of the important jobs of our operating system is going to be to map these pages or map physical memory to pages, are also called virtual address spaces, using address translation tables or page tables, and then manage them. So paging, there's different kinds of paging. We have read-only pages, and that is kind of what I described. It allows the page. One thing, the cool thing that it does is it basically means that you can't edit what's going on the page. So it allows you to map the page to multiple virtual address spaces while still retaining its integrity, so it doesn't get messed up. So that's one thing you can do with read-only pages. Another protection system is system-only, which is for like drivers in the kernel, stuff that you don't want being messed up. That's reserved specifically for the system, so it has like a user hierarchy. And then and those are called supervisor pages. And finally, the last one, not the last one, but an important one, I guess, is called demand paged virtual memory, and this takes multiple virtual address spaces and maps them to smaller regions of physical memory, selectively choosing what memory is mapped and what memory is swapped to the hard drive. So you could have, like, let's just say a gigabyte of virtual address space, but if only some of and then mapped to like 512 megabytes, and whatever is in memory at the time is determined based on frequency of use. So if you have like an application that's running and you have some data or whatever that the application pulls from every now and then, that data might be swapped out to the hard drive if you need to make way for other memory, or if the application needs other memory that wasn't being used, right? So then it will swap back from the hard drive. So it's communication between memory and the hard drive, basically. And it's a nice way to make your memory usage a little bit smaller while still keeping the computer relatively fast. And we're not going to discuss algorithms or whatever for doing that right now. We're just going to set up paging, and so we can do that kind of thing later in the kernel. So the ways that paging can be used, we need to talk about how to convert physical memory pages through a process called page translation. And since we're concerned with just long mode, we're not going through protected mode. We're going to worry about legacy mode, or we won't worry about legacy mode rather, or protected mode. We'll just go through long mode, yeah. So PAE, physical address extension, PAE paging is what we're going to use, and that's what's used in long mode. And it's organized into, it's a one big structure organized or separated into 4 tables. And each entry for each table has 8 bytes, and the top level structure is called the page map level 4 table. And this contains 512 page directory pointer tables, which is the second level. And each page directory pointer table contains 512 page directory tables, which contains 512 page tables, which contains 512 virtual or physical memory spots, that are 4 kilobytes in length. And 4 kilobytes as an SI unit, so 4,000 bytes, not 4 kibibytes. Anyway, the result of all this is that in 64-bit mode or long mode, we can support up to 256 good lord, 256 kilobytes. Oh my. Scratch all of that. 256 terabytes of RAM, or tebibytes? I don't know. It's not an SI unit tera, it's the computer unit tera, tebi, I don't know. By the way, future reference, little k is SI unit, big K is computer unit. That's the best way I can describe it. So little k is kila, or kilo, SI, big K is kibi, or computer, kibibytes. Yeah. Computer, yeah, okay. That's as far as I'm going with that. Anyway, before we start coding, last thing we need to talk about is how to do this in assembly. So the CR3 register, control register 3, is what we're going to be using. What it does is it stores the location of the highest level translation table, which is the PML4T, page map level 4 translation table. So the way we want to do this is as follows. First, we want to clear the table, or clear the space in memory in which the table is going to be stored. In our case, there shouldn't be anything in there in the first place, but just a sanity check, make sure that everything's out. Second, we want to set up our tables to point to one another, right? So we want our page map level 4 table. We want the first. We want the 0th index of the page map level 4 table to point to a page directory table. I'm sorry, did I say that? We want it to point to a page directory pointer table, and we want the first index of that page directory pointer table to point to a page directory table, so on and so forth. So then the last thing we need to do is we're just going to identity map out 2 megabytes, which happens to be one whole page table. So that should get us started. As I mentioned earlier, we'll really get going with paging and memory management in the kernel, but to get us into long mode, this will more than suffice. So first, let's clear the tables. So let's go into main.asm, come all the way down here, check lm. Alright, the first thing before we do that is we need to disable interrupts. Because if we don't, then when we start flipping long mode bits and all that stuff, it's going to think that there's interrupts enabled, and it won't find an IDT, or also known as an interrupt descriptor table, and it'll triple fault and we'll have issues. So first we need to disable our interrupts. And second, then we need to figure out where we want our page tables to be located. So OSDEV puts them as 0x1000, which is 4 kilobytes in, and that seems pretty decent to me. I like that. It works for me. And the reason is, if we look at our memory map, our low memory map, this is called everything from 0 to 1 megabyte, which is what this is right here, is called low memory. And we loaded our boot sector at 7C00. Now 1000 is a little bit lower than that. So here's 0x500. 1000 is in here somewhere. And that still leaves us plenty of stack space. It's not like we just load up the stack with stuff. So I'm not concerned about impeding on stack space. And that allows us to also freely build up our boot sector, which once again shouldn't be too big of a deal. We could probably put it up here, but I like what OSDEV does. It's simple, it's straightforward, so that's what we're going to do. So the way we're going to clear out memory, this is a pretty common way to clear out many things, is we're going to use a loop called repeat, which the command form of that is rep, repeat, I don't know. And the way that works is it repeats command for ECX number of times. ECX is our counting register. So what the command we're gonna use is store string, and we want it to be of size D. Of size D word. So we're going to use stosd, that's the command, store string D word. And so a D word is 32 bits, right? So 32 bits divided by 8 is 4 bytes. And we have 4 tables that we need to clear out. Each table has 512 entries. So let's do some math here. So 512 times 4. And each entry, well, 512, each entry is 8 bytes long, so 512 times 8. That's 4096, so that's how many bytes of entries we're going to have, and for one table. And there's 4 tables, so times 4. So that's 16,384 bytes, and a D word is 4 bytes, right? Because 32 divided by 8 is 4, so just divide by 4 again. So 4 times 4 divided by 4 is just times 1. So that means that we have to iterate this 4,096 times. So what we're going to do is stosd, that's how I pronounce it. If you pronounce it another way, that's fine. You get the idea. Store string D word writes whatever the contents of EAX is into the memory location as outlined by EDI. So if we put let's just, I guess, start with EDI. We want our tables to start at 0x1000, right? 4 kilobytes in. So let's move EDI to 0x1000. And we need to set our control register 3 to that as well, because remember, control register 3 is what holds the location of our page, of our highest level page table, which is can be at 0x1000 or 4 kilobytes in. So move into control register 3 EDI, and we want to write zeros because we want to clear out the memory space. So we're just going to nullify our EAX register, set it to 0, and we want to count 4096 times, as I mentioned, so move ECX to 4096 and rep stosd. Alright, so what that's going to do is that's going to write zeros, because EAX is 0. That's basically going to write 4096 D words of 0 into memory starting at location 0x1000. And since EDI changes as each repetition occurs, we have to set EDI back to 3000 or back to 0x1000. So now we need to look at how we want our page tables to be structured. So I'm just going to do that so I have some space. All right. So what we have here is we have our page map level 4 table is located at 0x1000, right? We want our page directory pointer table to be located at then 0x2000. Our page directory table will be located at 0x3000, and our page table will be located at 0x4000. Because if we look at this, the difference between here is 4 kilobytes, or kibibytes, right? This is kibibytes, not kilobytes. I keep misspeaking. It's an important difference. The difference is 4 kibibytes, right? Because we start at 1000 and go to 2000. And each entry is 8 bytes long, and there's 512 of them, which is 4 kibibytes. So that means that once our page map level 4 table ends, our page directory pointer table picks right up. So now we need to figure out how to get them to point to each other, right? Because we want our page map level 4 table to point to our page directory pointer table, which we want to point to our page directory table, which we want to point to our page table. So what we need to do is we're going to use a size directive, and a size directive is a little different. So normally we would say something like move, AX1 or something like that. A size directive specifies the exact size of the data you want to move into the register. So if it's AX, right, then we would be moving in a word. So if you move into AX1, 1 is a 1-bit value. But and if you moved that into a location like EDI, for example, which is what we're going to be doing, then that's only taking up 1 bit of space in EDI. Right, it's not taking up hardly anything. But if you want things to be evenly spaced, that's not going to cut it. You have to specify that you want a certain amount of size for each value you put in. So if you wanted to move something into AX, you would say move word AX1. So that ensures now that you're moving, well, it'd be like a destination, rather, a pointer. Whoops. So that ensures that EDI, or you're putting one whole word into that location instead of just one. And we're looking to move D words, which are 32 bits. So what we want to do is we want EDI right now is at 0x1000. That's where we last left it, which is at the head or the bottom of our page map level 4 table. And we want that to point to our page directory pointer table. So in other words, we want the first word, D word, of our page map level 4 table to reference a page directory pointer table. So what we're going to do with that then is we can move a D word. Move D word into the memory location at EDI. So we're moving this into memory specified by EDI, which is 0x1000, 0x2003. And also, we're using a 3 here because with page tables, the first 2 bits are set. So we just make it 2003. But so that way, our page map level 4 table at 0x1000 at that memory location is referencing or is pointing to our page directory pointer table at 0x2000. See how that works? So then all we have to do now is add to EDI 0x1000 and move on to our page directory pointer table, pointing to our page directory table. So let's move D word EDI 0x3003. So now EDI is pointing at 0x2000 because we added 1000 onto it. We want it to be pointing to our page directory table. Add EDI 0x1000. Yep. Move D word EDI 0x 4003 1000. Okay. So now EDI is pointing at the very end of our page table. So hopefully that makes sense. It makes sense to me. If it doesn't make sense to you, you can read about it in OSDEV and other places, but that makes sense to me. So now that we've got our structure set up here, we need to identity map the first two mebibytes, right? So that's the first 2048 kibibytes. And so in other words, we're going to identify the first page table. That's what we're doing. To do that, basically we're mapping physical address now to our page tables. EBX, which is the register we're going to use, we want to move this as a 8-byte, let's see, it's a D word, 3. And once again, we use 3 for the same reason we use 3 up here. We're effectively starting to map the beginning of our code. And we are going to repeat this. We're going to do this 512 times once for each entry. Whoops, 512. Okay. And then we're going to use a new kind of loop. So the best way I can describe this is it's similar to a for loop. The command itself is loop. And unlike repeat, it loops back to a label. So let's set our label right here, set entry. And it does it ECX times, right? ECX is our counting register. I probably should have mentioned that first. So it's doing it 512 times. So now what we need to do is we need to move dword, EDI, EBX. So we're now mapping the beginning at 0. We're now mapping that to our page table. And then we need to add 4 kilobytes to EBX because that's the size of each entry. So add EBX 0x1000. And we need to add to EDI, whoops, 8, so that we advance to the next page, or to the next entry in the page table. And that is it. So loop.setEntry, and this will then go back up here until ECX is 0. And with that, the first 2 megabytes are mapped. So as I mentioned earlier, this is going to suffice for us for now, but we will deal with this later in the kernel, like more complex memory management algorithms. So now all that's really left to do is enable the 6th bit, which is bit number 5, in control register 4. So if we go ahead and we look at control register 4, registers over here, control register 0, 4. Looking at bit 5, that is the physical address extension bit. So what that does is it tells the CPU that we're using PAE paging. So like segments, if you recall, we can't directly change the value of a segment. We have to have kind of an intermediate register do it for us. The same is true with control registers. So and of course, you saw that up here, but we used EDI as the same thing anyway, so it may not have been clear, but just so you're clear, we have to use an intermediate register here. So let's use EAX, control register 4. And now we can change the value of it by changing the value of EAX. Let's set the 5th bit. And then let's put that back into control register 4. Okay, so now we know that PAE paging, the CPU knows that we're using PAE paging. We're closer and closer to getting into compatibility mode now, which gives us 64-bit address space, but only 32-bit and 16-bit commands. So now we need to look at how we can activate long mode and activate paging. So we're going to use what's called the EFR register, or the Extended Feature Enabled register, which is a model-specific register in MSR. And assembly has a command that allows you to copy the contents of an MSR into EAX, and that's called RDMSR, read MSR. And depending on the value in ECX, it will copy EFR, our EFR register. And the value in ECX required to do so is 0xC followed by 5 zeros, 1, 2, 3, 4, 5, 80. Alright, so simple enough. Now we just need to read MSR. So now the contents of our EFR register are copied to EAX, and we need to flip the 8th bit. So let's take a look at the EFR register real quick. If we scroll down here, we see our EFR register. Bit 8 is our long mode enable bit. So if we flip that, then that will enable long mode. So let's OR EAX1, flip the 8th bit, and let's write it back with RWR MSR, so write MSR. Alright, so now that that's set, the last order of business here is we need to finally enable paging, and we need to enable protected mode, because even though we're technically not going through protected mode in the sense that we're setting up a protected mode global descriptor table and all that, we still have to go through it to get to long mode, even if it's just a stepping stone. So to do that, we need to look at control register 0. So let's go back up here to control register 0, and protected mode enable is the 0th bit, and paging is the 31st bit. So if we set this to 1 and set this to 1, then paging will be enabled and will be in protected mode. So let's go ahead and edit it as we did with CR4. And let's set the 31st bit and set the 0th bit. And then let's move back into CR4 EAX. And that's it. So now we're in compatibility mode. And to get into long mode, we need to set up a GDT, which is what we're going to do next. So let's create our GDT with gdt.asm. Before we start coding, it's best that you have at least a little understanding of what a GDT is. So a global descriptor table, GDT, is a table made up of segment descriptors. And a segment descriptor, as defined on page 67 of the AMD 64 Programmer's Manual Volume 2, quote, describes a segment, helpful, including its location in virtual address space, its size, protection characteristics, and other attributes. So what we're really interested in here is its protection characteristics and its paging or virtual memory characteristics, parameters, whatever you want to call them. And the fact of the matter is, in the 64-bit long mode or whatever, a majority of the GDT is ignored because the GDT is largely a protected mode thing. In protected mode, you still use segments. There's no segmenting in long mode. So the GDT largely serves the purpose in protected mode of protecting segments so that you don't get memory interference, which is basically what we're doing with PAE. So that's why a lot of it's not used, but some of it is used, which helps us identify or helps us establish protections for pages, which is why it's important we need to use it. So there are 3 descriptors. I'm not going to go into a whole lot of details, but there are 3 descriptors in our GDT that we need to discuss. There's the mandatory null descriptor, in which everything is set to 0. There is a code descriptor, and there is a data descriptor. So first, let's set up our mandatory null descriptor. So let's create our GDT label here that marks the start of our global descriptor table. And let's create our null pointer. And let's define it minus GDT. So I'm just simply saying it is equal to, this is the way the pointers work. It's equal to our current location minus GDT. If we look at the general, come over here as data. If we look at our general descriptor layout, you can see we have a segment limit, base address, another base address, some various bits, another segment limits, more various bits, and base address. None of that's important because, as you can see, some of it's grayed out, some of it's not. Everything that's grayed out, we do not care about. The long mode just ignores it. So for the null descriptor, we don't really care about any of these anyway because we're just going to set them to 0. But we're going to split this up into 1, 2, 3, 4, 5, 6 distinct parts. We're going to have 2 words here, and then 4 bytes. So let's set words equal to 0. Alright, so basically we're just now making these 0. The first byte is 0. We're going to treat this as the second byte. We'll later on in our code descriptors and our data descriptors, we will assign these bitwise, but for now we'll just treat it as a conglomerate or a consolidated byte. Then we have 1 more byte, and then the last one. So that's the null descriptor, arguably the easiest one. Next we have our code descriptor. Okay. So the code descriptor is organized as such, as I just mentioned. The bytes that the bits we're interested in here is the p bit. That's our present bit. The privilege bit, which we'll set to 0. These are 2 bits, 0, 0, and they have to do with security rings or privilege rings. And I'll put a link in that in the description. I'm not going to get into it in too much detail here, other than I'll just say that when they're both set to 0, it's set to maximum security, basically. So it's kernel only. And then these mandatory ones we'll set, even though it's ignored, we'll set them anyway. And then this is a we want this set to 0 because we only want the ring we assign it to be able to read it and execute it and basically deal with it. So let's go ahead and get that put in. So DW0, DW0, and DB0, right, because those are ignored. And then we'll assign this byte with a binary number. So DB00, so let's see, what do we want to assign? 0. I'm sorry, I have the wrong one. 1, 0, 0. Right, so we want 1, 0, 0, 1, 1, 0, and then everything else is zeros. Binary. And then this, the only bit we're concerned with here is L, and what that is it basically means, yes, we're in long mode, so it's a long mode bit. We want that to be 1, so 0, 0, 1, 0, 0, 0, 0, B, okay. And then DB0, because the last byte is ignored. Data. to the next section, GDT, and go about doing the same thing, db0. So the data descriptor is down here, and there's only one bit that we care about, and it's the present bit. So we're going to set it, and that's about it. So db 1, 2, 3, 4, 5, 6, 7, 8, db 0, db 0. Okay. And the last thing we have is our pointer. So the way loadGDT works is you feed it a pointer like this, or a label, whatever you want to call it, and the first thing it looks for is the size of the global descriptor table. So we'll have minus GDT minus 1. And then the next thing it looks for is its location in memory. And since we're in 64-bit memory, we'll use a keyword and GDT. That's, remember, the head of our table. So that's where it starts. Alright, so that's our global descriptor table. And implementing is super easy. So let's go back into main.ism. What we want to do here is we want to run lgdt, which is our loadGDT, and gdt.pointer. Yep. And then finally, so that loads our GDT, and then finally we will make the long jump. So once the descriptor table is loaded, all you have to do is then make a far jump, which just means that you're changing segments. So at the top, our segment was set to 0, where with our offset loaded to 7C0. So just change segments, and we'll change it to our code segment. So we'll make the jump from gdt.code to long mode, gdt.asm. And we want to put those in front of our 64-bit code because they're not meant to run in 64 bits. They're meant to run in 16. So if you say bit 64 above them, then you'll get a triple fault error and you're going to be all over the place. So don't do that. And then finally, create a long mode label. And we're basically in long mode at this point. So if there's any errors, they will show themselves now. 109. Oh, whoops. Insert, move might help. Okay. And nothing's happening because we haven't told it to. So to get confirmation that we're actually in long mode, let's try printing something in 64 bits. So to do that, printing things is a little bit different. We don't have BIOS to help us with interrupts and stuff anymore. We have to do it all ourselves. So part of the kernel is just writing functions to do simple stuff like that. But for what we want to do, it's not going to be too complicated. This is just confirmation, really. The way memory, or you have to print things in 64 bits, instead of calling an interrupt like intx10, you just load RAX, which is the 64-bit version of EAX, into video memory, which is located at B8000. So if we create a video memory pointer, vidmem pointer, or like our constant rather, at 0xb8000, then we can reference that and not have to worry about it too much, especially if we're going to do like a rep or something to clear the screen. So let's just try printing like a character or something to the screen so we can at least see what's going on. To do that, we're going to move into RAX. We have to move in the hexadecimal code for it. So if we come over here, this is a hex converter. I guess I'll put that in the description or something. But if we want to print like a T or something, the hex for T is 54. So if we just say 54, that's not going to work, because now we're in what's called VGA mode, which means that before we had a default that we couldn't really change, or we weren't concerned about changing at least, that had a black foreground and a light gray, or black background and a light gray foreground. But whereas we only needed one nibble in order to print a character, but now we need a full byte because we need to select the background and the foreground, and that precedes whatever text you're putting in. So the first character is the background, and the second, or the first, did I say nibble? I meant the first nibble is the background, second nibble is the foreground. I didn't mean nibble, I meant byte. We need 2 bytes now, sorry. So let's just make it a black background, and we can make it white text or something, so it's easy to see contrast. So a black background is 0 and a white text is F, so let's just make it 0F. So that means that to print a white T on a black background, it's moving into RAX 0F54. And vidmem RAX. We probably don't need to use RAX here. It's just 16 bits of information versus 64, but we'll use it later. It's clear. Clear. Okay. Oh, whoops. Let's get rid of the halt. W. Okay. Make. Okay, there we go. So it's 64 bits, so yeah. It's 64 bits, so it has space enough to print out 4 characters, and since I didn't specify anything to print out, it's just printing out nothing, so that's why it's covering these up. But you can see that we're printing out a T. That's clearly lighter than light gray. So to clear the screen, which might be something that we would inevitably want to do, we can print out, like, if we want to decide on a unique background color, because we're tired of seeing black for some reason. If we go like blue or something, that's pretty common. Then background code for that is 1. And if we want white text, it's F. So we could say 1F, and a space, coincidentally, is 20. It's not a coincidence, but anyway, the space is 20, so the full character for white text on a blue background for a space is 1F20. And you have to do that 4 times. F20, 1F20, 1F20. That's 64 bits. And it will print out blue text on a, well, there's no text because it's a space, but it prints out the blue background for sure. So it turns out that there's space enough for 20 of those with the default resolution. And make a long story short, if you print out 500 of them, then it'll clear the whole screen. So all we have to do is use our repeat command and load into EDI our video memory pointer. RAX is there, and then specify ECX, move ECX 500. Want it to go 500 times. And rep stas Q, because we're dealing with 64 bits now. And it clears the screen and makes it blue. So then, furthermore, if we then wanted to print like test or something on the screen, figure out what test is, then hex, whoops, test, convert. So it's 56, 65, 73, 74. And the way actually it puts it into memory is a little weird. So you have to record it, put it in backwards because it will shift it over. So in order for it to read left to right at least, so you put in the last character first, and that's what it prints first. And you put in the next character and it moves it over, moves it over, moves it over, so then you end up getting test the right way over. So first let's do 74, so move into RAX. Let's go 1F, 0x1F 74, 1F 73, or 1F 65, and 1F 54. And move into vidmem RIX. Test. Look at that. So this is just like basic 64-bit code, and when we start writing, or when we strap the kernel and start writing C, then we'll recreate that in C and do it properly. But that's just a nice confirmation that it's actually working and everything's happening correctly. So yeah, I guess that's pretty much it. So it's a lot of info, but you'll probably be able to figure it out. So yeah, that's all.